Solving the linear program. Many algorithms for handling combinatorial options or special cases of combinatorial options start by solving the linear programming relaxation of the problem, shown in section 11.3.1. A very useful and surprising property of demand queries is that they allow solving the linear programming relaxation efficiency. This is surprising since the linear program has an exponential number of variables. The basic idea is to solve the dual linear program using the ellipsoid method. The dual program has a polynomial number of variables but an exponential number of constraints. The ellipsoid algorithm runs in polynomial time even on such programs, provided that a separation oracle is given for the set of constraints. Surprisingly, such a separation oracle can be implemented by presenting a single demand query to each of the bidders. Consider the linear programming relaxation LPR for the winner determination problem in combinatorial auctions presented in section 11.3. Theorem 11.24. LPR can be solved in polynomial time in n, m, and the number of bits of precision t using only demand queries with item prices. Proof: consider the dual linear program DLPR presented in section 11.3, equations 11.8 to 11.9. Notice that the dual problem has exactly n plus m variables, but an exponential number of constraints. Recall that a separation oracle for the ellipsoid method, when given a possible solution, either confirms that it is a feasible solution or responds with a constraint that is violated by the possible solution. Consider a possible solution U arrow P arrow for the dual program. We can rewrite constraint 11.8 of the dual program as UI, which is greater than or equals to Vi of S minus the summations of Pj summing for all j in S. Now a demand query to bidder I with prices Pj reveals exactly the set S that maximizes the RHS of the previous inequality. Thus, in order to check whether the tuple of U arrow P arrow is feasible, it suffices to 1. Query each bidder I for his demand Di under the prices Pj to check only the n constraints Ui plus the summations of Pj summing for all j in Di, which is greater than or equals to Vi of Di, where Vi of Di can be simulated using a polynomial sequence of demand queries as was previously observed. If none of these are violated, then we are assured that the tuple U arrow P arrow is feasible. Otherwise, we get a violated constraint. What is left to be shown is how the Primo program can be solved. Recall that the Primo program has an exponential number of variables. Since the ellipsoid algorithm runs in polynomial time, it encounters only a polynomial number of constraints during its operation. Clearly, if all other constraints were removed from the dual program, it would still have the same solution. Adding constraints can only decrease the space of feasible solutions. Now take the reduced dual where only the constraints encountered exist and look at its dual. It will have the same solution as the original dual and hence of the original primal, but with a polynomial number of variables. Thus, it can be solved in polynomial time, and this solution clearly solves the original primal program, setting all other variables to be 0.